Hello dear students of +1 medical, non-medical respected teachers and dear friends. In this video I am going to discuss formation of stationary or standing waves in a stretched string. How stationary or standing waves are produced in a stretched string. Now what are stationary waves or standing waves? When two waves of same frequency, same wavelength, same amplitude but traveling in the opposite direction between two fixed points superimposed upon each other, then stationary waves or standing waves are produced. They are so called because there is no net onward motion takes place. So for example, stationary waves produced in a stretched string between two fixed points. So if the two interfering waves are transverse in nature, the stationary waves so produced are called transverse stationary waves. And if the interfering waves are longitudinal in nature, then the stationary waves so produced are known as longitudinal stationary waves. For example, stationary waves or standing waves produced in organ pipes. So in this video I am going to discuss stationary waves produced in a stretched string. So suppose we have a stretched string fixed between 2 points n1 and n5. Now divide this part into 4 parts so that we have n1, n2, n3, n4, n5, 5 points at equal distances. Now suppose at t is equal to 0, an incident wave, dark line, travels like this and reflected wave travels in the backward direction shown by dotted line just above the incident line because amplitude is same, wavelength is same, frequency is same. Then it means at t is equal to 0, crest of one is falling upon crest of other, crest of incident wave is falling upon crest of reflected wave, and similarly trough of incident wave is falling upon trough of reflected wave. So therefore we get resultant wave like this because amplitudes are added when crest falls upon crest. Now what happens at t is equal to t by 4? No, incident wave is traveling from left to right, reflected wave is traveling from right to left. So it means after time t is equal to t by 4, incident wave moves towards right by distance equal to lambda by 4 and reflected wave moves towards left by lambda by 4. So we get these two rays like this, incident wave and this is reflected wave. Now resultant will be a straight line. So it means string is passing through the mean position at t is equal to t by 4. Then at t is equal to t by 2, again incident wave moves towards right by lambda by 4, reflected wave moves towards left by lambda by 4, and we get this is the incident wave, again reflected wave, crest is one is falling upon crest of other, trough is falling upon trough of other. So but it is reverse of this first case. So again we get resultant wave which is the sum of the two like this. At t is equal to 3t by 4. T is equal to 3t by 4. And this is at t is equal to t. At t is equal to 3t by 4. Again instant wave after every time is equal to t by 4. Instant wave moves towards right by lambda by 4. Reflected wave moves towards left by lambda by 4. And again this is the situation. Crest is falling upon trough of other. So we get again a straight line. So string goes up, then down, then come back, then again passes the mean position. So again at t is equal to t, incident wave, reflected wave, this is the resultant. So it means we see this from this graph that during the formation of stationary waves, crests and troughs disappear and appear. As a result, we will see the loops like this, number of loops. So there will be 4 loops if we have taken 4 points. So 4 loops like this, And these points N1, N5, fixed point are always nodes. They are called nodes. So N1, N2, N3, N4, N5 are called nodes, whereas A1, A2, A3, A4 are called antinodes. So it means stationary waves are produced in the form of loops, but no onward motion takes place, and it forms nodes and antinodes. Now what are nodes? So nodes are the points where amplitude is minimum and strain is maximum. In other words, nodes are permanently at rest, whereas antinodes are points where amplitude is maximum and strain is minimum. So this is how nodes and antinodes are formed during the formation of stationary or standing waves in a stretched string. Now, from this we can discuss the various modes of vibrations of a stretched string. First of all, suppose when string of length L vibrates in a single segment, it vibrates as a whole. So when we pluck at the middle, it vibrates as a whole like this. There is only one loop. And suppose lambda is the wavelength of the wave, nu is the frequency. This is called fundamental frequency when string vibrates in a single mode as a whole. So then if we find relation between wavelength and length of the string, so it comes out to be half wave. So lambda by 2 is equal to L, or lambda is equal to 2L. So by definition we have velocity, formula of velocity v is equal to u lambda for any wave, transverse or longitudinal. So therefore nu is given by v upon lambda, fundamental equation, or now lambda is equal to L and v is equal to under root T by m by sorry velocity of transverse waves. So T is the tensional string, m is the mass per unit length. So this is the required expression for fundamental frequency of vibration of a stretched string, which is given by nu is equal to 1.2L under root T by m. From this fundamental equation, this is called fundamental frequency also, and this is called first harmonic also, first harmonic of stationary waves. So we can make various laws of vibrations in a stretched string. Number one, law of length. Fundamental frequency is inversely equal to length of the string, or we can say that nu L remains constant, or nu 1 L1 is equal to nu 2 L2. So more is the length, less is the frequency, and vice versa. This is the law of length. Then law of mass per unit length. Fundamental frequency is inversely proportional to square root of mass per unit length. Now, as m is equal to mass per unit length, so mass can be written as volume into density upon length. Volume can be written as area of crossing length into rho into upon length. Length cancels, or area of crossing is given by pi d square by 4, because d is the diameter of the stretched string. So m comes out to pi d square by 4 into rho, or if substitute value of m in this equation, number 1, so we get nu is equal to 1.2L under root 4t pi d square rho, or nu is equal to 1.LD under root t by pi rho. So from this we can separate this law of mass per unit length into two more laws. Number 1, nu is inversely proportional to d, and nu is inversely proportional to square root of density. So this is also known as law of diameter. It states that fundamental frequency is inversely proportional to diameter of the string. Number 2, law of density. So fundamental frequency is inversely proportional to square root of density of the material of the string. So it means, so this is law of mass per length. Then law of tension, because fundamental frequency is directly proportional to square root of tension in the string. Tension stretching force, or you can say nu is proportional to square root of t, or nu square is proportional to t, or nu square upon t is constant, is always constant. So these are the various laws of vibrations in a stretched string. This question may be asked individually. Now, what happens when string vibrates in two segments? Same length L we have taken, but we divided it in two segments, equal segments, so we get two loops like this. Now we have 1, 2, 3 nodes and 2 antinodes. So wavelength changes. Let lambda 1 is equal to wavelength of the wave so produced when string vibrates in two segments. So then lambda 1 will be equal to L, because full wave is produced, or nu 1 is equal to V upon lambda 1, or nu 1 is equal to V upon L multiplied by divided by 2. So it comes out to be, So 2 times, so new one comes at 2 times 1.2L into T by M, or 2 times new, or new one is equal to 2 times new. It means when string vibrates in 2 segments, wavelength changes. That have taken lambda 1 as wavelength. Frequency also changes. So new one is equal to 2 times the fundamental frequency. So this new one is known as second harmonic. So second harmonic is 2 times the fundamental frequency or first harmonic. Similarly, when string vibrates in 3 segments, so L will be equal to 3 lambda by 2, 3 lambda 2 by 2, or lambda 2 is 2L by 3, and we have 4 nodes, 3 antinodes, and again we get nu 2 is equal to 3 times nu. So in this case, frequency of third harmonic is equal to 3 times the frequency of first harmonic, and so on. For n segments, first for n segments, so nu n minus 1 is equal to n times nu, because for 2 segments we have nu 1 is equal to 2 nu. For 3 segments we have nu 2 is equal to 3 nu, and for n segments we have nu n minus 1 is equal to n nu, or for n plus 1 segments we can have nu n is equal to nu plus 1 into nu. This nu 1, nu 2, nu 3, they are called overtones. It means second harmonic is the first overtone, third harmonic is the second overtone, and nth harmonic is the n minus 1th overtone. So these show overtones, and n plus 1th harmonic is the nth overtone. So harmonics are nu, nu 1, nu 2, nu 3, and so on, whereas overtones are the harmonics other than fundamental frequency. So this is all about formation of stationary waves or standing waves in a stretched string, and how harmonics and different overtones are produced. It is, you can say that the harmonics are integral multiple of the fundamental frequency. So harmonics produced in a stretched string or a wire is equal to integral multiple of the fundamental frequency or first harmonic. So this is all about standing waves or stationary waves produced in a stretched string. So till next video, stay tuned, be happy, all the best, good luck.